Hello. Today I want to talk about one of the fundamental results in combinatorics, the fundamental principle of counting. It says that if A and B are finite sets, how can you get the size of the Cartesian product of A with B? Well, it's just the product of the size of A with the size of B, right? So if you look at it this way, it's in an example, it's just saying how many ordered pairs can you form from the elements of each set. Well, you multiply the number of elements of each set. So an example of this, you could say if A, just to do a very small example, say A had the elements 1, 2, 3, and B has the elements A and B. Well, let's not use A and B since our sets are called A and B. Let's say here M and N, just for the sake of picking two letters, right? Then what could you form from these? If these are your sets A and B, then you could imagine labeling, do a little table, right? And label A, the elements of A as the rows, and you can imagine labeling the columns by the elements of B, right? And right, so we'll put A in the rows, we'll put the elements of B in the columns, right? And then what could you label in the cells? You just put all the elements of this table would have all the elements of the Cartesian product A cross B, right? So I could put 1 comma M, right? 2 comma M, 3 comma M, 1 comma N, 2 comma N, and 3 comma N. And there we have we could see the 6, right? Which is the size of A cross B is in fact the size of A times the size of B, which is 3 times 2, right? So this is just witnessing that result in an example. So there we're just saying, you have number of rows, number of columns. When you make all how many cells then are in that table, right? Well, it's the number of rows times the number of columns is all this is saying. This is written in our set theory notation. So this is one example of that. Another way to look at this is to say if this is a sort of an alternate statement. It's not saying anything different mathematically, but sometimes it's helpful to just think of it this way in a lot of the contexts where it gets used. So an alternate formulation of the fundamental principle of counting, right, is you could say if A and B are independent events, and we'll get to what that means in a sec, right? If they represent independent events, and what's an event? Well, you can say in a probability theory course, you would define that really carefully. Here we're just we'll see more through example what kind of thing we're talking about. But if A and B are independent events, where A has n outcomes, right? So that's the number of outcomes for A, and B has m outcomes. So n and m here just represent natural numbers that count the number of possibilities, right? Then you can think of the events A and B together have the two events together. That single event, which is comprised of those two events, has n times m ways of occurring, or we could say n times n outcomes, right? N times n different outcomes. This sometimes is a helpful way to think of the fundamental principle of counting in a lot of the contexts where it's used. So you can think of, for example, here is another way to think of it. Suppose I had a deli, right? And let's say event A is pick my bread. So this is a very simple deli. We're just going to do two things, right? We're going to I'm going to pick my bread, right? So that will be our event A. And we'll let event B be pick my which meat we want on our sandwich, right? And let's say then a particular deli has, let's say, rye, white, or wheat for our bread options. And for our meat options, let's say we have turkey and ham, right? Then you can ask, how many different sandwich orders are there at this deli, right? And you can think of this as exactly the same as what we had up here, right? It's just instead of calling it 1, 2, 3 and MN, which were just sort of arbitrary names, now they mean something right now. 1, 2, 3 is, bread option number 1, bread option number 2, and bread option number 3. And our N and M is now N is meat option letter N and meat option letter M, right? So besides that, it's exactly the same question as up here, right? You're doing pairs of bread, comma, meat, and that builds your sandwiches. So you could draw out exactly the same table, but now each cell in the table corresponds to selling a sandwich or buying a sandwich, I guess is how I framed it here. Yeah, each cell in the table corresponds to a sandwich order, right? So 1, comma, M, for example, would be turkey on rye, right? So that would be a way or sorry, ham on rye, right? Would be 1, comma, M. So that would be a way to have a correspondence between those, right? So you could say those are the 6, right? There's 2 times 3 equals 6 sandwiches, right? Now, one thing I want to talk about a bit is in this example, this idea of independence, right? So what do I mean by independent? I mean that I can mix and match any bread with any meat, right? There isn't some restriction at the deli that says, if you pick white, then you're not allowed to pick ham anymore, or right, that there isn't some, I don't somehow limit my options for B based on what happened with A. So that's where independent comes in, right? Independent means I can mix and match however I like. So this is a little example with 2 events, right? One comment that I want to make here is, so this is sort of a follow-up, is that this little way of thinking of it as a table, it kind of breaks down if you have 3 or more events. In theory, you could still do the table, but now with 3 events, it's going to become a stack of tables, right? You need another axis to put your 3rd event on. So suppose I have not just rye, white, and wheat, not just turkey, ham, but let's say I also have now, they vastly improved their selection at this deli. And we can choose a condiment, right? They took their customer feedback very seriously. That was saying that the sandwiches were a little plain and more choice was necessary. So say we have mayo or mustard now for our sandwich, and let's call this event C is picking picking one, right? So you can pick 1 bread, 1 meat, and 1 condiment is how we're going to order our sandwich. So this becomes harder to represent with this table, right? Because now you would need sort of 3 axes, right? You'd have event A, right? So we have our rye, white, or wheat, right? You'd have event B, which would be the turkey or ham. And so you still have down here, you still have, these 6 cells representing our 6 sandwiches, like we described before, right? So you have, this would be, rye, this would be turkey on rye, right? This would be white bread with turkey. This would be ham on rye, and so on, right? So that's the, that would be just event A and B, and so on, writing out the others, right? But now we have axis C, right? We need another axis sort of going perpendicular to these, right? So here I have my, this is my meat axis, my bread axis. Now I would have to have an axis C, and then along this axis C, now I have, I have up here, I'm going to have the mayo grid, and then down here I'm going to have the mustard grid, right? And it gets sort of picture pretty quickly. It gets pretty cluttered, right? This is only with 2, and now you have these tiles down here, right? So I'd have 6 tiles down here that correspond to the 6 tiles up above, right? And it kind of gets hard to see and hard to read, and but now you'd have, so this top slice of 6 would be, rye, ham, mayo, rye, turkey, mayo, right? It would be all the ones with mayo. And then on the bottom, you'd have sandwiches like down here, I would have, say this tile right there would be wheat bread with turkey and mustard, right? It would be that sandwich. So so this, you'd have sort of 2 of these tiles of these 2 by 3 tiles, right? But visually representing it this way gets really awkward, especially what if there's a 4th event, right? What if this picky eater deli goes way out on a limb and starts offering lettuce, tomato, or onion, right? Then now we need a 4th dimension that we don't have, right? So point being, this table way of representing it sometimes is really nice, especially if you only have 2 events. It can be really nice like this, right? It can be really efficient, but in general, it breaks down, right? Notice though, the number still works just fine. The number of sandwiches, that you can extend the fundamental principle of counting by still just multiplying, right? You can still just say, well, it's the size of A times the size of B times the size of C, because I'm allowed to mix and match the options from A with the options from B, which the options from C in any way I choose, right? So I get 3 times 2 times 2, right? So I have 12 different sandwiches. So just like you can multiply 2 events, you can multiply 3 if they're independent. What I also want to show though is, because this visual representation is cumbersome on its best day, I want to show another representation that sometimes is easier when there are, especially if there are 3 or more events. So you could do it like this. You could say, instead of a table, you could do a tree. And the way you could draw a tree is you say, okay, event A, what do I have for event A? I have rye, white, or wheat for event A. Those are my options, right? And now these I'm going to mix and match in every possible way with the options for event B. And event B tells me that from my rye, I could pick ham or turkey, right? From my white, I can pick ham or turkey. And from my wheat, I can pick ham or turkey, right? That then takes me to event C. And with event C, then I can pick mayo or mustard, right, from the choice of rye and ham. I can pick mayo or mustard from the choice of rye and turkey, right? I can pick mayo and mustard from the choice of white with ham, and so on, right? So I get mayo and mustard for each of these. And now you can actually see all 12 options, right, in a diagram that's not so cluttered, right? Right. What are the 12 sandwiches? They're right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? There we have our 12 sandwiches, right? And each sandwich just corresponds to a path in this tree from a root to a leaf, right? So for example, this path right here, if I did, right, if I did rye with turkey and mustard, right, that's sandwich number 4, right? Sandwich number 4 is, there we go, right, turkey and mustard on rye. That would be sandwich number 4 in this scheme, right? Because every path through the tree from left to right, because these are trees that grow on vertical faces and grow outwards this way, right? But you can imagine turning it 90 degrees if you want to think of it more as root to leaf. But yeah, every path through the tree, right, is corresponds to a unique sandwich, right? So that's what's nice about this is you can then iterate this, right, through multiple events. So this, right, we were able to multiply a number of outcomes of A times the number of outcomes of B times the number of outcomes of C. So let's do a little bit more complicated example, and one where the number of outcomes is a lot larger, and one where we're certainly not going to write out all the outcomes, not in the table, not in the tree, but we can still do the count anyway. So let's do this. How many 4-digit pins exist, right? So think about your debit card, right? A debit card has typically associated with it, to use a debit card, a 4-digit pin, right? And so you're going to do a digit 0 through 9, a digit 0 through 9, a digit 0 through 9, digits 0 through 9. And I just want to know how many pins are there, right? How secure of a system is this, right? If I just pick up someone's debit card that fell out of their pocket, how likely is it I could just guess their pin? Is it pretty likely? Are there not very many, or are there a huge number where it would really be difficult to guess their pin? Well, let's think about this. Let's think about event A. When you chose your pin, what's the first thing you had to do? Well, let's say event A is pick the first digit of your pin, right? Let's say event B is pick the second digit of your pin, right? Event C is pick your third digit, and event D is pick your fourth digit, right? And how many options? 0 through 9 for each of these, right? So if I could pick out of 0 through 9 for each of my events, then what do I have? I have 10 options in each case, right? There are 9 numbers from 1 through 9. So then with 0, that's 1 extra, right? It's 10. So I have 10 options for each of these. And so then what can I say? Well, the total number of pins, if I have to go through all 4 of these events and select the 4 digits in my pin, then I have, what would the number of pins be? The number of pins would be the product of the size of all of these sets, right? Would be 10 times 10 times 10 times 10, right? It's just the product of all the number of options, which would be 10,000. So that would be the number of 4-digit pins. If you think about that, is not really that many, right? If you do find someone's debit card laying on the ground and you're totally unscrupulous, right? When you just try running it and guessing, something at random, you have a 1 in 10,000 chance of being summoned, apparently. But maybe we should wrap up. Maybe it's a credit card fraud investigation coming to get me. Yeah, it's only a 1 in 10,000 chance, right? Which is way bigger than, say, chance of winning the lottery, right? So, yeah, kind of kind of strange when you think about it. So, all right. So there is our example of right, 4 digits, all selected 0 through 9, right, is just 10 times 10 times 10 times 10, right? So there we have fundamental principle of counting, right? A really tiny example, just slightly larger where that little table kind of doesn't look so good anymore. And then a much more complicated example, right? One where I don't want to list this out in a tree or a table. I mean, you can imagine what the tree would look like. Event A would look like 0, 1, 2, 3. This would be just event A, right? 5 up to 9. But then for each of these, now you got to do event B, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right. And then for each of those, you have to do event C. And then for each of those, you have to do event D. Right. So you're not going to draw out the table for this. But the cool thing is we can still get the number, right? Even without drawing the table, we can still get how many. So, all right, great. There's the fundamental principle of counting. See you soon for more counting. This is tip of the iceberg. We're going to do a lot more counting tricks from here.